Okay, so today we're going to look at the derivative of y equals b to the x. So let's take an example for, say, y equals 2 to the x. And let's figure out what its derivative would be. We're going to take the ln of both sides. So I can rewrite this as ln y, and I'm going to bring x ln 2 down. Now I want to take the derivative of both sides. Well, I'm going to write dy by dx, and we learned yesterday, or the day before, that the derivative of ln x is 1 over x. So I'm going to write the derivative of ln y as the derivative with respect to x, 1 over y. And I want to take the derivative of x ln 2. Well, if we look on our calculators, and we want to see what ln 2 is, we can say ln of 2 is, we can see it's about 0.693. Well, we know then it's just a number. So if I say the original function is something like 2 to the x, then its derivative is just 2. So if I want to take the derivative of x ln 2, then its derivative is just ln 2. I'm going to solve for dy by dx, which means I'm going to bring y to the other side, so I get y ln 2. Well, I already know what y equals from back here. Y equals 2 to the x. So I'm going to replace y with 2 to the x. So there's the derivative. Which means that if I look at a general function, for example, b to the x, I can say that its derivative is b to the x ln b, where b is whatever base we have chosen for the question. So let's look at an example. Let's say y equals 5 to the x. Well, I can say its derivative follows this pattern, which would mean it is 5 to the x ln 5. If you want to do something with a little more complicated, for example, 10 to the power of 3x minus 2, let's use the chain rule. So I'm going to say the outside term is 10 to the x, which makes the inside term 3x minus 2. If I do the derivative of this, I know this is 10x ln 10, and the derivative of this is 3. Plugging those into the chain rule, I can say that it is h prime g prime of h of x. Let's look at another one. For example, 13 to the power of root x. I can say that the outside term is 13x, and the inside term is root x. Well, the derivative of this is 13x to the power of x ln 13. And the derivative of this is 1/2 x to the negative 1/2. Putting those together, I'm going to use dy by dx this time. I can say that it is h prime g prime h of x. And I can simplify this I get 13 to the power of root x ln 13 all over 2 root x. Let's look at 23 to the power of 4x minus 7 all to the power of 5. So the outside term is 23 to the x, the inside term is 4x minus 7 to the power of 5. If I take this derivative, I get 23x ln 23, and the derivative of this part is 4x minus 7 all to the power of 4 times 4, which simplifies to 20 times 4x minus 7 to the power of 4. Putting it all together, h prime times g prime h of x. So we need to look maybe now for a shortcut which will help us as we move forward with more complicated functions, for example the power rule or the quotient rule. So if we look for the pattern, we can say that if the original function is b to some power g of x, which is a function, we can say that maybe a shortcut, f prime of x, is equal to the derivative of g of x, which is g prime of x, times b to the g of x ln b. This proves helpful if in our last example when we're looking for the product rule. So we can say that a of x is x squared and b of x is 2 to the x. A prime of x is equal to 2x and b prime of x is equal to 2 to the x ln 2. So the derivative dy by dx can be found using a prime b of x plus a of x b prime. Then I can look for a common factor. There's an x in both terms and a 2x in both. So I'm going to pull out x 2 to the x. From this first term, I'm left with a 2. And from the second term, I'm left with x ln 2.